Hi, I'm Randall Hayman, a maths academic. I'm using my YouTube channel to make quick turnaround videos on mathematical problems and concepts. So if you're a lecturer, tutor, high school, primary school teacher, parent, grandparent, or student, and you'd like me to make a video for you or your students, use the comment section below the video. Okay, so this is part 2, where we're answering this here. Well, we're proving this. This is for Benny Lowe in California. Okay, so what we did was, just to recap, we said that if D is an integral domain, then D is a ring. So that means that dx is a ring. So it will just suffice now to show three things: commutativity. We have to show that dx has a multiplicative unit, and we have to show that dx has no zero divisors. And I did the commutative part in part 1. So we're now up to the multiplicative unit. So let's have a look at that. So to do that, next, let's call it hx equals 1. Well, but it's the same really as 1 plus a1 x1 plus dot, 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 whatever, with ai is equal to 0 for I greater than 1, I greater than or equal to 1. So it's equal. So this is an element of dx. So it's the polynomial, and so that's that. Next, that equals that, what can we say now? We could say that fx times this special polynomial hx is equal to, I suppose if you wanted to do them, it's obvious that if you multiply a polynomial by 1, you get the same polynomial. But I suppose using what we had before, you could go I equals 0 to infinity. We called it ai xi. We could multiply that times 1, and that equals 1 times this, which equals hx. Well, actually, and it equals that. So you really have to show that fx times 1 is equal to 1, and 1 times fx is equal to 1. So I've done that all in all of that. And so that equals fx. Yeah. I suppose what you could do here is you could write here equals hx, which is the 1 times fx. I've been a bit confusing because I've swapped between hx and fx, but look, that's good enough. That's good enough. So that's, that's proven. So I'll just write that in actually. So dx has a multiplicative unit. Now look, if this is all a bit confusing, look, let's just write this in red and then I'll get rid of blue and I'll get rid of it. All this is saying is that if you take, say d was the integers, well, all this is saying is if you have a 3x squared plus 2, that's a polynomial, you multiply it by 1, that's equal to 1 times 3x squared plus 2, which is equal to 3x squared plus 2. That's all it's saying. That's all it's saying. And it works for any polynomial. So there's nothing particularly clever here. It's just the way it's worded. Okay, now finally, now we need to show, this is the hard one. Finally, we need to show that dx has no zero divisors. In fact, I might just to be clear, because this gets a bit complicated. Finally, we need to show that dx has no zero divisors. So what does that actually mean? That is, if fx and gx are elements of this integer domain, and fx times gx equals 0, then either fx equals 0 or gx equals 0. Okay. So I think this time I'll go let fx equal a0 plus a1 x1 plus all the way up to am xm. I think this time it might be a bit more easy if we use this notation. And here ai equals 0. No, sorry. AI, sorry about all this. It's getting a bit late in the night. And all the coefficients are element of the integral domain. And let's just put that m is a positive integer. So that's, or 0. And we'll let gx equal b0 plus b1 x1. Now remember, f and g could have different degrees, so we can't put an m here. We'll have to put an n or something like that. I'll put an n. Oh, sorry, that's a b, isn't it? Actually, let's write the whole thing out so I get it nice and clear. b n x n b I. You could here put for all I if you wanted to, but n is an element of z plus union. So both m and n are positive integers. Okay. So let's assume, suppose fx times gx equals 0. Let me just raise this up a bit now. Okay, so, whoops. This is a bit cunning, this little proof, this bit. So I'll twist this around. So I'll put the 0 here equals, so what I'm saying is 0 equals fx times gx equals a0 plus a1 x1, x to the power 1 plus am x to the n times b0 plus b1 x1. So this equals a0 b0 plus ... other terms. Okay. Now let's have a think about this. So this is a polynomial. This here is the only constant coefficient. In other words, there's no x power here. Everything else will have an x power. So if 0 equals all of this, it must be that, therefore, 0 must equal a0, b0. Now, since a0 and b0 are elements of D, an integral domain, we have, so, sorry, let's write domain, integral domain. Well, because it's an integral domain, D, it has no non-zero divisors. So it has no zero divisors, to be precise. So that means that this is the key bit. Then either A0 equals 0 or B0 equals 0. That's the key step. Key step. Yeah, it's an integral domain, and that's one of the conditions for an integral domain. So now I've got to pick one of them. It really doesn't matter which one I pick. So we often use this term: without loss of generality, let A0 equal 0. I could do case A and case B. Case A is A0 equals 0, case B, B0 equals 0, and work through them that way. But this is a much neater way to do it. So what I can do is now I can replace up here, I can replace that with 0. So what I'm saying is that equals, I'll write it in so you can see it, 0, because I know A0 equals 0 now. A1, X1. This is a really cute proof, this actually. Whoops. Sorry, I've done a lot of these videos today. I'm getting tired. It's getting late. Reward myself with an episode of Seinfeld soon. Okay, so this bit here, the 0 drops out, and these are all divisible by x. So what I could do is I could write x a1 plus a2x 1 plus am. Now I've divided this by x, so I'll get x to the m minus 1 times b0. Okay. Now I can divide both sides by x. Okay. Okay, so now we've got a situation that's similar to, let's go back up here, this process up here. So I might actually mark that with an, actually I've got colors, so that's quite nice. I'll put a, now I can go back to this. So repeating the logic, from this bit here. So now here we know A1 times B0 equals 0. So A1 B0 equals 0, and hence A1 equals 0 or B0 equals 0. So we can repeat this or these steps at each time. So every time we do this, we show that one of the coefficients is equal to 0. Each time showing that one of the A, I, or BI coefficients equals 0. So if we keep doing it, eventually we will show that AI equals 0 for all 0 is less than I is less than M, or BI equals 0, all the B's are 0. So for all 0 is less than I is less than or equal to N. So then either fx equals 0 or gx equals 0. Clever, huh? So that means, this means that dx has no 0 divisors. So we've done the 3 things that we needed to show. So if you want, we could just put this completes the proof. And if I was marking this, I'd give it a big tick. Okay, that's all I wanted to say. Any questions on anything I've done here, just drop me a comment or send me an email. And if you've got any other questions about mathematics, do the same.